All right, so we talked about CDMA last time, and we said that the chips or the codes that are used by the different nodes A and B, these have two important characteristics. One is that each key is highly correlated with itself. So when you multiply by itself, the value will be high, and when we multiply it by others, the value is zero. And also, even if we have some missynchronization, if the key is shifted, then when you multiply it with itself, also the correlation will be very low. And this is what we tried when the key was wrong. It was not actually wrong; it was actually shifted a little bit. So the data was not decoded correctly. So we also discussed the issue that the CDMA has certain disadvantages, and one of them is the fact that some nodes, or at least the base station, if we're talking about point to multi-point communication in a star topology where the nodes have to communicate with the base station, so at least the base station has to have all the keys of all the nodes in order to be able to receive data from all these nodes. In which case, the base station has to manage several keys, which complicates the design of the transceiver at the base station, right? So one one possible solution for this particular issue, where they use actually one key for all the nodes. So the idea in this spread Aloha multiple axis is to combine Aloha with CDMA. So use Aloha to simplify the transceiver design, and use CDMA to provide multiple access. But here, what happens is that of course, because Aloha has low efficiency, in the sense that if two nodes are sending at the same time, the collision will happen, right? And the collision actually reduces the efficiency of the transmission, right? So what happens is that the nodes themselves, they use one single key. Okay? So they use one single CDMA key. Okay? So what happens here is that the sender A will generate the key using a particular clock, and generates the key at a certain point in time. Okay? B uses the same key,
but a different time.
So this means that if you have transmission overlapping like this, okay, it depends how the receiver generates the key. If the receiver generates a key that is synchronized with the key from A, it will be able to receive A correctly, even if there is overlap.
But it should be synchronized.
It should be synchronized. That's the issue. So it has to be synchronized with A.
So it looks only at the initial time.
Exactly. It looks at the time where the key is generated from A, and it has to generate the key at the receiver in synchronization with the key from A, in which case it can actually receive the data from A, and B for it will be like a noise that can be extracted easily. Because remember, only when the key is synchronized, the correlation will be very high. If the key is shifted, then the correlation will be very low. So the correlation with B, because it's not synchronized, so the key is not synchronized, so even though it's the same key, remember, it's the same key, right? But I use it if C, for example, if node C wants to receive the data from A, it will generate the key synchronized with the key that's generated from A, in which case the correlation with B will be extremely low. And it will be able to extract the data that is sent by A, even though there is some overlap. So CDMA will allow me to have multiple access, because if I don't have the CDMA, then this is basically ALUHA, which means that there is a collision. So CDMA is combined with ALUHA to increase the efficiency, because if I don't use CDMA, then the efficiency would be very low. And if I use complete CDMA, then I have some scalability issue, because the transceiver has to maintain all the keys. So by combining the two, we can use one single key, and we can separate the different traffic by using this feature of high correlation if the key is synchronized. If the key is not synchronized, then the correlation will be very low. So that's the trade-off now. Okay? Any questions?
So the transmission is between the nodes. It's
right.
It's not involving the.
Even if there is a base station, it uses one single key. All the system uses the same key. So any node wants to receive from any node, then the node will have to generate the key in synchronization with this other node. That's the only way that it can receive the traffic from this particular node. And all the other traffic from all the other nodes for it will be very low correlated, because it's not in sync. If A and B send at the exact same time, then there is a problem.
Yes.
So in that case, you cannot extract A from B using the same key. You cannot. And in that case, only there will be a collision. So in that case only, we cannot extract A from B using that system. So this system actually facilitates the multi-access if A and B are not sending at the same time. If they are sending at the same time, then this is still a collision. So this table here summarizes all the multi-access techniques that we have discussed. Not all of them, some in categories, in the 4 different categories. As we said, there is a space domain multiple access, where we use directional antennas to separate the traffic from multiple nodes, in which case you can have concurrent transmission using 2 different directions or 3 different directions. And for that, we discussed sectorized antennas in the physical layer, which can facilitate this type of multiple access techniques. So in that case, here, only one terminal can be active in one sector. So in certain direction, in one sector, only one node can be active. If you have 2 nodes, then there is a collision, because the only way for me to have channel access is through the space division multiple access. So if you have 2 nodes sending at the same direction, they will collide. But if you have 2 nodes sending at 2 different directions, then it's fine. Okay. So they will not interfere with each other. So this is useful for cell structure using directed antennas or sectorized antennas. It's very simple, and it increases the capacity per kilometer, of course, as we said before, because you are directing all the energy of the signal towards a certain direction, rather than just sending in all directions, in which case the energy will be divided by all the 360 degrees. Mm-hmm. Okay, so here you are directing the power in certain direction. So in the case of TDMA, on the other side, as we said, the segment sending time in two different disjoint time slots, in which case the disadvantage here is the synchronization. So one issue is the synchronization, and that's why in many cases there are guard spaces between these time slots to facilitate any clock drift. So especially in the uplink, when multiple nodes are trying to send at different time slots, you need to have guard spaces because each node sends based on its own clock, which is independent from all the other clocks. So if I don't have proper synchronization, then the nodes might overlap, in which case there is a collision. Okay, and because TDMA wants to eliminate collision, we have some guard spaces. So we have to have synchronization techniques, and also we have to have guard spaces. Both of them can facilitate the TDMA to work fine. In the standards, it's usually used joint or in addition to or use TDMA and FDMA. An example for this is the GSM and many of the 3G and 4G standards. They use a combination of TDMA and FDMA, and in 4G we actually use OFDMA.
Yes,
Right? So FDMA we divide based on the frequency, and then we use filtering at the receiver node to basically filter the transmission for a particular node. And in CDMA we use the codes, orthogonal codes, or if we use the single code, then we have to have some kind of asynchronous transmission where the two nodes cannot send at the exact same time if we want to use the same key. Okay. Okay. So let's just load and I hope I already put it. Already, okay. Okay. Okay.
Just you can start.
Yeah, this will resume. Okay. So again, here we said that this is the definition of the radio resource management, and these are the parameters that we can change, and the objective is just to try to optimize the use of the resources to fulfill these objectives, which in many cases are conflicting objectives. And then we try to find the trade-off. So these are the basic resources that we have. These are the direct physical layer resources that we have. We have spectrum in terms of channels, we have time slots, we have codes, and we have power. Okay? Or in other words, energy. طيب. So let's consider one simple example, and from here we will have to talk about a little bit of math. So we will consider a simple wireless network having one base station and two mobile users. So this is a very, very simple scenario, and we can show you that from the radio resource management point of view, this scenario is complicated enough. So this simple scenario will allow you to understand the trade-offs that we're talking about. So, so we have two users. Some of the, one user is far and one user is close, something like this. So each user has a different gain, and this gain is dictated by the H, and H here is the channel gain for this particular user. And this H incorporates two possible components. The path loss is dependent on the distance, right? And possibly fading. Fading due to the fact that you have different fading characteristics based on the existence of obstacles and so on and so forth. Dr. Muhammad last time also talked about this channel gain H. Okay, so H can incorporate the path loss and the fading. So depending on this, we have a specific gain, and this is actually the path loss gain. So here H refers to the fading, and DI refers to the path loss, and you have the gain for the transmitter antenna and the receiver antenna. Okay, usually those are fixed. So depending on DI, the user might have a specific gain, which is good or bad. Okay, so that's the scenario. So how can we calculate
Alpha then.
alpha?
Yeah.
Alpha is the path loss component or the path loss exponent. They call it the path loss exponent, which is usually around 2.5 or 3. As we said before, alpha is the path loss exponent. Only in the vacuum it's 2, but the typical value for this is close to 3, 2.5 to 3. Okay, so Shannon actually estimates or tries to estimate the rate experienced by a certain user, which is basically the W is the bandwidth multiplied by log to 1 plus the signal to noise ratio. Okay, so this equation gives you the ultimate rate that is achieved by a user who is not experiencing any interference from other nodes. Okay, and only experiencing path loss and fading from from obstacles or something like this. So we can have here in this gain, we can have path loss and fading or fading. Okay, so PI is actually the transmission power from the base station to user 1 or from the base station to user 2. Okay, which means that PI times the gain is the received power. Okay, is the received power divided by the noise. So this is actually the signal to noise ratio. So this is Shannon's equation.
N is what? No.
The N0 is the noise multiplied by the noise
By the band.
multiplied by the band. Right? So this is basically the equation. So simply, if this is the rate for node I, then what do we need to do? Here, we assume a very simple scenario. Remember, we don't have any interference. We are using 2 separate subchannels. Okay? And the base station can send to the 2 users or 3 users or whatever, okay, without having any collision or something. They send on 2 different frequencies. So the only limitation here is what? Is that the base station has a certain power budget, and it needs to split this power budget between the 2 users. Right? That's the only constraint now. So I need to split the power, because at certain point I'm allowed to send with maximum amount of power. And because I'm sending to 2 different users on 2 different frequencies, I have to split the power. So now, should I split it equally? Well, that's one possible thing.
No, based on the distance. If it's
Or proportional based on the distance. And if it's proportional based on the distance, okay, how? What
Like
is
the
what is the
far-
criteria? The far will
more
get
power.
will get more power. Yeah, sure. Well, if you get more power, well, what you have to think about what is you're trying to optimize. What is your objective?
Getting less signal to noise rate.
You have to think about your objective
more,
now.
More throughput.
Okay. You have to well, if your objective is to maximize the throughput, then define mathematically the throughput, the aggregate throughput, and then optimize it based on certain criteria. So that's exactly what we will try to do. So what is P1 and what is P2?
Be assigned to node 1 and node 2.
بالظبط.
Since we do have two nodes.
Exactly. So what is P1 and P2? Well, one idea is to be very simple and divide the power equally between the users. So will this actually give you the best option or the best solution? Let's see. Numerically, if we assume that P, اللي هي maximum power, is 5 watts and W is 100 kilohertz, G1 and G2 are like this, okay? Which means that here the user 1 will have better gain.
Right.
User 1 will have better gain, which means that user 1 is probably closer or is having less fading.
Right.
So when I look at G1 and G2, I should actually conclude that it's not the best way to divide the power equally between the two users, right? So as you can see, if I divide the power equally, which means I give 2.5 watts to user 1, 2.5 watts to user 2. So this will be the rates based on basically the
Equation for
so 100 kilohertz log 2 1 plus 2.5 multiplied by 1.5 divided by
100
100
10 to the power minus
3 times 10 to the power minus 5. So this is for user 1 and this is the result. So for user 2, the difference here will be this is 0.5, right? And this is the result. So that's how you calculate the rate. So in which case, this is the rate and this is the total rate, 3.41. This is the good thing about that is that I don't have to think. It's simple. Divide the power by the number of users. But this is not the maximum. Okay? Well, but sometimes it's good. It's good enough, as we will see. The other thing is that let's try to maximize the throughput. So what we'll try to do is that we will try to maximize R1 plus R2. These are the decision variables of your optimization. So we're trying to design now P1 and P2, which means that the outcome of this optimization problem is to know the value for P1 and P2. Okay? This is subject to the fact that P1 plus P2 is less than the power budget, less than the total budget. And the fact that P1 and P2 are not negative numbers. Usually these constraints are not they do not affect the solution that much. So if the function, so before we solve this problem, we have to learn one important thing. Solving an optimization problem could be tricky if this optimization problem does not have one minimum point. Like sometimes, if the function R1 plus R2, which is what we're trying to maximize now, if this function is something like this, so in that case, this function has no, like it has more than one minimum point.
Right.
But the global minimum point is this. But this one is we call it a local minimum.
Yes.
So usually dealing with these types of functions is extremely tricky. Extremely tricky. Okay? This is what you do actually as part of the neural network when you do like the search and stuff. This is what you're trying to do. Even when you look for weights, you're trying to minimize certain function, and the weights are your decision variables.
Right.
Except that you don't do that. The tools will do it for you. But this is exactly what happens inside. So in more than 95% of the cases, you have to first of all prove that your function is convex. So what is convex? Convex here talks about the fact that the function that you're trying to maximize or minimize has one minimum or one maximum, which means that something like this is not there. If your function is convex, then you can simply get the derivative and you can solve the function from there. Because if you say that dfx dx equals 0, this actually gives you all the possible points where the function has a slope of 0, or the tangent has a slope of 0. So all these functions have this point.
Right.
So so dealing with such situation is going to be very tricky, and it may lead you to, because the actual, in real life, the actual functions that look like this are much more complicated, and then you get multiple local minima, and these local minima are numerical, and it's very hard to achieve. So it's in many cases very, very hard to get the global minimum amongst all these local minima, except with very, very sophisticated techniques. So in radio resource management, people resort to using convex optimization. Convex optimization is a big class of optimization, where the function that you're trying to maximize or minimize has one minimum or one maximum. Okay, and of course one minimum as a function of the decision variable. Okay, which means that basically you have one point for optimality. You have 1 point for optimality, and the function is not non-convex like this, it's convex.
Okay.
The function that we are trying to optimize, R1 plus R2, usually logarithmic is convex. The logarithm is convex. And the addition of multiple logarithmic functions is actually convex. So this is good news. So if your function is convex, so all you need to do is just to get the derivative and to set it to 0.
0, and then we'll get the value.
A very simple function is x log x. So if we want, which looks like this, if we want to get the minimum point or the optimal point, we get the derivative of this, which is 1 plus log x, which means that if you get this here, if you get the -1 here, so x is 1 over e, which is this. If you put this here, so basically fx at minimum is minus 1 divided by e. Why? Because log 1 divided by e is minus log e, which is 1. Right? So if x is 1 divided by e, so 1 divided by e log 1 divided by e. Log 1 divided by e is actually minus log e. Right? You know that? Well, because log e to the power -1, for the log, the exponent gets out, right? So it's minus, yeah. So this actually is -1, because log e is 1, right? So the fx will be will be minus 1 over E. And E is actually 2.4, so 1 over E is around 0.4, so it's actually, it's somewhere here. Okay? Okay, so that's the, so luckily this function was convex, and we did not have any constraint. So if the problem has certain constraints, which is basically 100% of all the radio resource management problems, they have constraints because the resources for us are constraints. Like the power, we have power budget and we have to split it. So we have to have some constraints. So what if the problem has constraints? So we know if we have an optimal problem with no constraints and the problem is convex, then we use normal derivative to get the solution, which is what we did in the previous example. Here, this problem is constraint optimization. So a guy called Lagrange, he actually invented the technique of Lagrangian multiplier. By this we mean that if the problem is constraint problem, what we do is that we use something called Lagrangian multiplier to combine the constraint with the objective and make it unconstrained. Okay? So if we have a problem like this, we have an objective and a constraint, what we could do is that we will use a Lagrangian multiplier called lambda and get this constraint in this format here and add it to the objective. So this will be the Lagrangian function. And the Lagrangian function, it's the non-constrained version of the optimization problem. Okay? So according to certain theory, if the original objective, if the original problem is convex, which means that the objective is convex and all the constraints are also convex. Because the constraints are functions. They could be by the way non-convex. If the original problem is convex, the Lagrangian solution will be a solution for the original problem.
Will be solution for the
original problem.
So if you solve the Lagrangian, the solution that you get from solving the Lagrangian will be the solution for the original problem. Okay? But the condition for this is that the original problem has to be convex. That's why the class of convex optimization is very important.
Yeah, so that means that there is a way to convert unconvex to convex.
So that's that's another story. Some people they define a certain radio resource management problem, and then the problem turns out to be non-convex. So this is bad news. So this is bad news. So then they say, okay, so what do I do now? Because it's non-convex, so I cannot use these techniques. Well, there are certain ways, certain tricks to transform the non-convex optimization into another problem. Okay? These tricks, during the transformation, you can use certain approximation. Like, for example, one of the constraints is non-convex, and this is actually clearly making the entire problem very hard. Okay, so I will use certain approximation on this particular constraint to convert it to convex, which implies that there is a certain assumption that you have to make. For example, مثلا, this works only if the signal to noise ratio is high, this something like that. Based on this, you say, okay, I will not use the non-convex, I will transform it into convex through optimization. Sometimes the transformation will actually allow you to transform the problem into a different domain. by substituting the variables into other variables, something like this. It's a very long process. It's a very big. It's a science.
Yes.
Okay.
I read in on one of the papers that he converted non-convex to convex.
Right.
But what I mean that we can't use this in this
If
approach.
once after you transform the problem into a convex problem, only
Except in the
then you
original
can
one.
use only then you can use Lagrangian to join the convex constraints with the convex objective into a non-convex optimization, and then solve the Lagrangian problem, which will be the solution for the convex problem. Then you have to do the transformation back to the non-convex problem to get the solution for the non-convex problem.
Okay.
So any transformation that you do, you have to do it on the other way. Or if it's approximation, then خلاص, this is a solution based on approximation, which means that it's suboptimal.
Okay.
You cannot claim it's optimal. Okay? It's a huge area, and usually the work in these areas is the one that gets you to the journal in a shortcut, because it usually involves lots of math and things like that. So basically, if we have a convex problem like this, so this problem happens to be convex. Okay, so the objective is convex, and the constraint is convex. Usually the constraint, if it's linear, it's convex. Okay, so we combine the objective with the constraint using the Lagrangian multiplier. The idea of the Lagrangian multiplier is that, remember, we are using here minimization, right?
Right.
So the idea with the Lagrangian multiplier is that the Lagrangian multiplier will be perceived as a penalty. So if the constraint is not fulfilled, I will allow lambda to be high to give you a penalty, to act against you. You are trying to minimize, and I'm increasing I'm increasing the objective by adding a certain component. So lambda will become like a penalty. If you are maximizing, then lambda will be negative, so that again I will act against you. Okay, so that's the idea of the Lagrangian. So Lagrangian acts as a penalty. If your constraint is not achieved, this means that I will add certain penalty over the minimum function that you have. So this will allow the minimization to try to set this term to be zero.
Okay. This for the
And this
best
happens
X
when-
and Y.
Eh?
For the best X and Y.
Yes, and this happens when
we find the
when the condition is fulfilled, then lambda will be zero.
Okay.
So when the condition is fulfilled, lambda will be zero, which means that the minimization of the Lagrangian will be the minimization of the original problem. You see what I mean? So if the constraint is fulfilled, okay, if the constraint here is fulfilled, lambda will be zero, right? Which means that what I'm trying to minimize now is 2x squared plus y squared without this term, because lambda is zero, so zero is multiplied by anything is zero. Okay? Or if this is exactly the zero, if x plus y minus 1 is exactly zero, then it doesn't matter the value of lambda, right? It doesn't matter the value of lambda, right? So lambda, for this particular problem, because this is non-constraint now, so I can get the derivative with respect to x and y and lambda now, because lambda is another extra decision variable. And when I solve these three equations, I get x equal 1 over 3, y equal 2 over 3, and lambda is not 0 here. Why? Because if you add x to y,
Doesn't give one.
this will give 1, which
Okay.
means that here
Lambda should-
the constraint is fulfilled at the 0. Right? So x plus y, 1/3 plus 2/3 is 1.
Right.
So 1 minus 1 is
plus
0. So the constraint
plus
is
that.
fulfilled at the 0. So lambda is allowed to be anything now.
Okay.
But if the condition or the constraint is fulfilled at to be above 1, then the minimization will try to push the value of lambda to 0, towards 0, in order to the minimization will try to push this value towards lambda equals 0, so that this will be all 0, and the minimization of this Lagrangian will be the minimization of the original problem.
Wait, lambda should be the maximum. It's like a penalty, صح? Then we should maximize if it doesn't fulfill. So if x plus y does not equal to it's more than 1,
لا
then
if x plus 1, this means
x plus y.
this means the constraint is fulfilled.
Okay.
If x plus 1, if x
So
plus
we
y,
maximize,
if x plus y is more than 1, this means the constraint is fulfilled.
So we only
So-
maximize the value of lambda when it's less than 1.
Right, exactly.
Okay.
Right. Okay. So going back. So now we're supposed to have the proper tools, okay, to go back to the throughput maximization problem, because I told you, even though it's 2 users only, but it's not as easy as you think. So the problem now becomes the aggregate, because we said that we want to maximize R1 plus R2, right? And R1 is this, and R2 is this when I equal 2. So the aggregate throughput is the summation from 1 to 2 to the Shannon equation. And then the constraint is, remember, here na it's not plus, it's minus. Why?
The log with the minus of.
Why here is minus, is not plus?
We have to maximize.
Bravo, Alik. Yes, that's it. That's it. As we said, because we're trying to maximize,
The throughput.
yeah. So lambda will act against you, so we're trying to make it minus. Because in the previous example, we were trying to minimize,
minimize.
and that's why
Add
we
penalty.
add penalty.
Yeah.
Okay? So, so even then, by the way, it's not, well, you can try to derive, but it's not easy to derive this. But it's basically based on the fact that we get the derivative with respect to P1 and P2. So that's what we do. We get the derivative for P1 and P2, and then we set both to 0. It turns out that you will get 2 equations in 2 different unknowns, and the 2 equations are kind of mingled together, and it's not easy to solve. But the actual solution, so I will not ask you to derive this in the exam, because it's actually it's mathematically intensive a little bit. So basically, this is what we call water filling. So what happens is that the best PI in that case will be mu, and mu is actually a function of GI minus this mu is a function of both the channel condition for both users, okay, minus W times N node divided by GI, okay? So what happens is that mu acts as a water level. Mu here acts as a water level. The user who has a condition that the ratio between the noise and its own gain is less than mu, this means I can give some power to this user. If this condition is not fulfilled, which means that the gain, the ratio between the noise and the gain, okay, is above mu, which means that the noise is very high and the gain is very low,
Okay.
right? Which means that this user has a very bad channel. Really, really bad that it's above mu. And mu is like acts as a water level. If it's above mu, then it's better not to give any resources to that user at all. Okay? Which means that it's zero.
If mu is less than 1, then it is okay. You can allot resources to the...
If mu is less than 1,
we can allot resources, it is okay. The channel condition is good.
no, I didn't say that. No. If this value is positive,
Okay.
if this value is positive, mu is a specific water level,
Okay.
okay, and this gain is less than mu,
Okay.
okay, then you can get resources. You can get a little bit of resources proportional to the difference between the two.
Difference between which two?
Mu and this ratio, because this means that this ratio is this combination is actually positive, because if this ratio is above mu, this means that this is negative. Can you assign a negative power? You cannot,
No.
right? So you cannot assign a negative power. So this means that you will assign 0. What does that mean? This means that mu acts as like a certain water level. If you are below this water level, then we can give you more resources.
The value of
If you are above the water level, then we will not give you any resource, because in order for us to give you some amount of resources enough, we have to give you more than the maximum P. So mu here is a function of the maximum power, which is P1 plus P2. Okay?
it's not a function of the gain for both users. The gain is
The gain will be for the individual users. Mu here is actually a function of the maximum power, which is P1 plus P2, which is actually the maximum power. Because remember, P1 and P2, because they are the decision variable, the constraint is that P1 plus P2 is less than or equal to maximum power.
Right.
Okay, but mu here is a function
The
of the
maximum.
maximum power. Okay, so this is how it looks like. So all the users, assuming there are 2 users or even more, okay, will have a certain mu, and mu is actually a water level. If your channel gain, okay, in relation to the noise is below this water level, this means that we will give you this amount of resources, which is proportional to the difference between the water level and your channel gain at this point in time. So this is mu. Okay? And this is Wn node divided by Gi. So this part. Okay? So only if this part is positive, we can give you this amount of resources. If this part is negative, we will not give you anything. Because this means that your channel gain is extremely bad, and we cannot, in order for us to give you enough power so that we can get any throughput from you, is we have to give you more than the maximum power, which is not possible. Okay?
If it is below the water level, then no more resources can be allocated.
No, if it's below the water level like this one, this
Yeah.
means that we can get you all these resources.
Okay. In third time
Because
slot,
this means, remember, the green bars, if it's low, this means that you have very good condition.
Yes.
If it's high like this means that you have very bad condition.
Okay.
Huh? So the bar does not indicate how good, it indicates how bad. Okay? And it turns out, if you apply this rule and calculate the mu based on the maximum power, the actual optimal powers will be like this. Which means that the rates will be like this. Remember,
But we maximize the throughput by only
4 kilobits per second.
Yeah.
So that's a good observation.
so
That's why I told you, sometimes it's not
that's
even
really
worth it. That's why I told you, sometimes simple techniques might be good enough.
it might be good when the number of users is really high.
Exactly.
Then yes.
So, but remember, water filling, well, the mathematical derivation, assuming that the mathematical derivation is done offline, in terms of water filling technique, calculating mu is simple based on the maximum power. So you can calculate the water level and you can assign to each user, but still it's O of n. It's O of n. So you have to go through each user, and for each user calculate the gain, and then calculate the water level and give this user the amount of power based on the difference, and go to it's O of n. But if you divide equally, it's O of 1. So this means I don't have to calculate it for each user. I know the number of users.
Yes.
So the maximum power divided by n is the power for all of them. So it's O of 1. Okay, so so in a way, of course, if O of 1 can get me the solution much faster, and for this it's O of n and it gets me only 4 kilobits per second, it's not worth it. Okay, so that's how you so this is as far as it gets with mathematical derivations. Later on, it's not that intensive. But the idea again is just to define your objective, and here the objective is simply maximizing the throughput. Of course, we will talk about later the fact that maximizing the throughput is not the best thing that you can have, because maximizing throughput might not be fair. Okay, so how can we incorporate fairness into this? Okay. So we'll talk about that probably next time, because we need to give you the chance to we need to stop here.